In our first video on properties of the determinant, we looked at determinants of elementary matrices. We looked at determinants of an elementary matrix times another matrix. Here we're going to look at determinants of upper triangular matrices, determinants of transposes, and determinants of lower triangular matrices. So first of all, we want to look at an upper triangular matrix. Just do an example real quick. Say I have a determinant of the following matrix. Let's do a 4x4, make it fun, right? So I got 1, 2, 3, 4 across the first row. In the second row, 0, 5, 6, 7. Across the third row, 0, 0, 8, 9. And across the fourth row, 0, 0, 0, 10. So normally you say, 4x4 determinant, nasty dude, right? Well, actually, it's not so bad. You want to expand across the first column because there are a bunch of zeros in that column, right? 3 zeros. Let's do our signs, plus, minus, alternating. I'm going to start with the first entry of 1. And I'm going to cover up the first row in the first column and take the determinant of the submatrix that results from covering up the first row in the first column. It's going to give me 5, 6, 7, 0, 8, 9, 0, 0, 10. And I don't have to worry about expanding any further down that first column because you start with 0 on all of those entries. So next, I'm going to do a 1 times determinant. Well, how do we take the determinant? Hold up. Determinant of a 3x3 matrix. Well, we can go down the first column once again. First column because we got, 2 zeros there. So if I expand on the first column, I'm going to do signs plus, minus, plus. So we're going to start with the entry 5 there and multiply it by the determinant of the submatrix. When you cross out that first column, first row, and we get 8, 9, 0, 10. I'm going to go up here in the upper right corner. What do we have so far? Well, we have 1 times 5 times, okay, we got to find the determinant of the what matrix? 8, 9, 0, 10. That is a 2x2 matrix. We will do what? We take 8 times 10? That's going down the descending diagonal and multiply up the ascending diagonal, so minus 0 times 9 is 0. So it looks like in reality we're talking about 1 times 5 times 8 times 10. Now, what do you notice about those numbers? Well, we know, first of all, that the product here is, what is that? 1 times 5 is 5 times 8 is 40 times 400. So we know the answer's 400. But what about those numbers? What about those numbers 1, 5, 8, and 10? Well, you notice that those are the numbers on the main diagonal, the descending diagonal. So it turns out that when you have an upper triangular matrix, that the determinant is just going to be the product of the descending diagonal entries. So we're not going to prove that. We'll state the theorem. Here's the theorem. If A is an n by n upper triangular matrix, then the determinant of our upper triangular matrix is going to be the product of the descending diagonal. A11, A22, A33, and so on and so forth, A and n. So anytime you write a double subscript like that, the A11, A22, the repeated subscript, that is on the diagonal. Now, why are we not going to prove that? Well, some of you don't have a lot of experience with proving things rigorously. We would probably use proof by induction to prove this, if you're curious. Proof by induction. So we forego that proof, and we'll just state that. We'll go on to another situation. Let's look at transposing a matrix. Let's look at a 3 by 3 matrix. A. So we have 1, 3, 1, 0, 4, 1, 0, 5, 0. So that's my A matrix, and I want to look at A transposed. A transposed. So how does A transpose work? Well, you take the rows of A, make them the columns of A transpose. So 1, 3, 1 is going to become 1, 3, 1, the first column of AT. And the second row of A, which is 0, 4, 1, is going to become the second column of AT, 0, 4, 1. And the third row of A, 0, 5, 0, is going to become the third column of AT. Now let's look at their determinants. Determinant of A. Now how do I find the determinant of A nicely? Let's see, 1, 0, 0, 3, 4, 5, 1, 1, 0. Let's go down the first column. Why the first column? We got a bunch of zeros there, right? You got 2 zeros there. Let's do plus, minus, plus. So I'm going to start with entry 1 and multiply by the determinant of the submatrix. When you cover up the first row in the first column, I'm going to have what? 4, 1, 5, 0. It's going to give me 1 times the determinant of that, multiply down the descending. 4 times 0 is 4, minus up the ascending. 1 times 5 is 5. That's going to give me 1 times negative 1, which is negative 1. All right, let's do the determinant of AT. Determinant of AT. So that's 1, 3, 1 down the first column, 0, 4, 1 down the second column, and 0, 5, 0 down the third column. I'm going to expand across the first row because there are a bunch of zeros there, right? 2 zeros. Signs are going to be plus, minus, and plus. So I'm going to start with 1 and take the determinant of the submatrix that results from crossing out the first column in the first row, which is going to be 4, 1, 5, 0. And I'm not going to worry about expanding across those additional entries because they're just going to give us 0. So here we have what? 1 times, let's compute this determinant. 4 times 0 down the descending diagonal is 0, minus 1 times 5 up the ascending diagonal. And it looks like, right here, that we get negative 5. Negative 5. Yeah, so 1 times negative 5 is negative 5. Ooh, looks like I made a boo-boo earlier when I was doing the determinant of A. Let's go back and look at the determinant of A. I totally messed up, didn't I? So here, when I was doing 4 times 0, I was multiplying down the descending diagonal. This should have been a 0, which would have changed things a bit, right? 0 minus negative 5 would have been negative 5. And 1 times negative 5 would have been negative 5. Okay. Now we can circle our answer. That's correct. You'll notice that the determinants of the A and the A transpose are exactly the same, and that kind of should be intuitive. I mean, basically A transpose is just A, except you've changed the rows out with the columns. And remember, when you're taking the determinant of a matrix, it doesn't matter if you expand across a row or a column. So yeah, just be aware that A and A transpose have the same determinant. So I'm going to write that fact down. Let me write it down. Theorem. Determinant of A is equal to the determinant of A transposed. Very important fact. One more thing we want to look at. We want to look at lower triangular matrices. Lower triangular matrices. So let's say I want to find the determinant of a lower triangular matrix. 1, 2, 7, 0, 9, 11, 0, 0, 3. So I have a lower triangular matrix. Now, if I want to find the determinant of that, we know that matrices have the same determinant of their transpose. So what I'm going to do, I'm going to change this dude into its transpose. So the first row I'm going to make into the first column, 1, 0, 0. The second row I'm going to make into the second column, 2, 9, 0. And the third row I'm going to make into the third column, 7, 11, 3. So we're using the previous theorem. And wait a second, now we have an upper triangular matrix, and we know that for an upper triangular matrix, by our first result of the day, we just take the main diagonal and multiply those numbers together. 1 times 9 times 3, 27. So yeah, that means it's the product of the main diagonal again. It doesn't matter if it's upper triangular or triangular. In any case, it's going to be the product of the main descending diagonal. So we want to say that corollary, important corollary. A corollary is something that follows from previous results. So corollary, if A is n by n lower triangular matrix, then determinant of A is the product of the main diagonal entries, A11, A22, A33, so on and so forth, A and n. All right, I think that's it for now.